Okay, this is the second lecture on introduction of Cellular Automata. In last class, we have started Cellular Automata. We defined Cellular Automata, and we also gave example of a Cellular Automata called Game of Life. So before going further, let us recall what we have studied in last class. So cellular automaton is a quadruple, z to the power d, s, m, and r. So this z to the power d is called d-dimensional lattice, or here we love to call it cellular space, right? And you know that z is a set of integers, and d is called dimension, and s is a finite set of states, right? And m is called neighborhood vector. What is so? What is that? It says that for each v of z to the power d, right? So v plus vi, that also belongs to z to the power d is obvious, and this m is called neighborhood vector. This m actually, the neighbors of a cell is used, to get the rule or transition function, which is the next one, the r. R is from s to the power m to s, and this r is called transition function, but in C literature we call them local rule, or sometimes the simple rule of the C. And here this m is the the neighbors of a cell. So how can I find the neighbor? The previous point, the last point, it is written that for any v, suppose any v, when you want to apply this r, you should know the state of its neighbors, right? Because r takes the present state of its all neighbors, and then it goes to the next state. So it's called state transition. So how can I get the states of its neighbors? For that, I should know the neighbors. So I can know the neighbors using the neighborhood vector. Suppose v is my cell. Then v vector v plus vector vi, where I is any one to m. By adding that one, I can get the neighbor. I can get the neighbors of v. So in this way, I can get the all neighbors of a cell v, and then I can get the states of the neighbors, right? Then using those states, the present states as input, I can apply the local rule on the cell. Okay, so r transforms, r goes from s to the power m to s. So that we have discussed in last class, and then we introduced one term called configuration. So a configuration is nothing but assignment of states to the cells, right? We have say S, is the set of finite states. So any cell can have any of the states, any of these S, the all possible the possible states. So when we assign some state to the cells, then we get a configuration. So mathematically, configuration C is a mapping from z to the power d to s, right? So actually, the function C assigns the states to all the cells of the lattice of z to the power d, and from that we get interesting one. That so total number of functions s to the power z to the power d, that you understand. So s to the power z to the power d actually represents so all possible functions from z to the power d to s. Okay, so then when I get this one all possible configuration, then I can think of a CA as a function, right? CA is a quadruple, but when I get all these things, I can think of CA as a function which hops from one configuration to another configuration. So it's a function G. Sometimes we call it global transition function from s to the power z to the power d to s to the power z to the power d. So these things we have discussed in last class. So here,
Can
sure.
I ask a question? Okay. So here we are showing that R is s to the power m to s. So m is the number of neighbors, right?
Yeah,
So when we are transforming, we are also considering the cell itself.
right.
So should not it be like s to the power m plus 1 to s?
S to the power.
M plus 1 to s.
No, this m includes the itself.
Okay, but
This
when we are
m
defining,
includes,
okay, when we are defining the capital M, there we are considering v1 to vm is the
yes,
neighborhood vector. So in the neighborhood, when we are saying including that, right? In that
right,
case also.
right.
Okay.
Suppose v1 is 0, 0. So from in case of today, in the last class also I have shown that v say 0, 0 in 2D case. So if
Hmm.
I add v plus 0, 0, then it will be okay.
Okay.
But to be generally we assign this neighborhood vector. If you want, you may exclude 0, 0. But the what is done actually, so always the cell itself is included in a set of neighbors. Okay. This is the convention. But if you want,
Okay.
you can exclude.
Hmm.
Okay, is okay.
Yeah, this is fine.
Okay. So up to this we have discussed. Now let us concentrate on the configurations. Right here, configurations. A configuration is a mapping and assignment, and we have due to the power d number of cells, so infinite number of cells. So size of a configuration is always infinite, right? Size of configuration is always infinite, right? Because due to the power d itself infinite. However, although the configuration size they are infinite, we have special interest on two special types of configurations. So one is called finite configurations, another is called periodic configuration. Why we are interested on this kind of configurations? See, one thing we understand, configuration is infinite. Theoretically, I can assign any state to any cells. So practically, if you want to simulate something, it is really difficult to deal with the infinite configuration, right? So somehow we need for practical simulation, uh, practical implementation, we need something finite, right? So from that motivation, we are developing here, we are discussing here two things, two types of configurations. One is finite configuration, one is periodic configuration. So finite configuration we are going to discuss. So before that, let us designate a state Q as a quiescent state. What is that? A state Q in S is quiescent state if RQQ is equal to Q. Right? Means if you give is the argument of a function R or the function R so all Q, then the output is also Q. So it gives you some flavor of stability. Right? So if a cell, if it finds that all of its neighbors are in state Q, then the cell itself remains in state Q. So there is no transition. So let us designate a state Q as a quiescent state. So Q is there actually having this property. Now, if you have Q in your state set, then you can get finite configuration. What is that one? Suppose, as I've said, Q is a quiescent state. Then a configuration C is finite. If this set, you can see that X vector X of z to the power D, and where C of X, the configuration of X, okay, it is not Q. This set is finite. In simple words, that all a state is, a configuration is finite if all but a finite number of cells are in quiescent state. So only finite number of states, they can be in non-quiescent state. If it is so, then that configuration is called a finite configuration. So this takes an example. Suppose you have cellular space, so all are Q. The marked one, that is, suppose that is in non-quiescent state. But outside of this, the marked space, they all are in quiescent state. So from the figure we understand only finitely many cells are in non-quiescent state. If it is so, then this configuration is called finite configuration, right? You can recall that in the last class we were discussing, when we were discussing a game of life. The example we have given, in that case we have considered finite configurations only. Particularly, we can deal with the finite configurations, right? And when Van Neumann first developed the CA, in all the cases, they have considered, they dealt with finite configurations, right? So an interesting theorem: if initial configuration of the CA is finite, right? Suppose initial configuration of the CA is finite, then the CA remains in finite configurations forever. So no matter how much time you run the CA will always be in finite configurations. Proof is very simple, so we can prove it to induction. So suppose, I'm giving you an outline. Suppose at time t the configuration is finite, right? Now to go to from t to t plus 1, so all the cells, they apply the rule R. Now from the property of quiescent state, if a cell is in quiescent state and all the neighbors are in quiescent state, they will remain in quiescent state. So therefore, so the other cells, so where this condition is satisfied, there will be a quiescent state. Now since only a finite number of cells are non-quiescent state, right? Then in the next step, only these much steps, the deeper, the dark black lines I have drawn, only these much cells at most can be non-quiescent state, right? So t to t plus 1. So see here, sorry. So here, see outside of the boundary of that configuration, say they all are the the cells are in quiescent state, but the bounded cells. So in the bounded cells will feel that okay, some of the neighbors are in non-quiescent state. Then based on the rule, that cell may move to non-quiescent state. But a distant cell whose all cells are in quiescent state, that cannot move, that will remain in the quiescent state. So this one. So the next time step, only these much cells can be in non-quiescent state, right? And rest are in quiescent state. So therefore, it is again a finite configuration, right? It is again a finite configuration. Now you apply this. If you apply this argument, you will see that always the configuration will remain as finite, right? Now let us consider CF is set of all finite configurations. Okay, so C, our S to the power J to the power D is actually set of all configurations, and here I am extracting some some configurations from that set, and CF is set of all finite configurations, and it is obvious that CS is proper subset of S to the power J to the power D, right? It is proper subset of S to the power J to the power D. Now let GF be the restriction of G on the finite configuration. So G, recall that G is our global transition function, which is actually the CA. Now suppose in the domain of G is always CF. Okay, so I'm writing that function as GF, right? So that is written here. So GF with the set of with the restriction of G on the finite configurations, right? Then what I can get? Then I can get GF from CF to CF, right? So therefore, although G is our global transition function, from that function, when you have finite configurations, I can get another global transition function called GF, whose domain is finite configuration, and from the finite configuration, it moves to another finite configuration. So this relation is useful, and that is used. We shall consider it later. Now come to the next class of next special type of configuration called periodic configuration. So before defining so, let us define a shift function, right? Shift function, its name suggests, it's if you consider one-dimensional case, it just left shifts, nothing else. Okay, so it translates the configurations, right? Translate the configurations in a coordinate direction. So we are considering D shift functions. Subscript I is telling us the shift function in direction I. So we have D, D dimension, so D directions are there, right? So I have D shift functions, right? Sigma 1, sigma 2, and sigma D, right? So let us take an example. So D equal to 1, right? So then if I write C dash equal to sigma 1 of C, what does it mean? It actually means, the configuration, the C dash, actually nothing but a left shift of C, right? Nothing but, suppose all 0, 1, then all 0. If you, put sigma 1 by sigma 1 and to me, just 1 is left shifted in one position. So now if I write sigma 1 square, what does it mean? So it is twice, left shifted twice. Sigma 1 cube, left shifted thrice in this way, right? So now with this, with these functions, we can define the periodic configuration. A configuration is periodic if it is invariant under D linearly independent translations. It is the definition of periodic configuration. A configuration is given, if you consider a small part, and if you, perform the translation, then you see that is invariant. does it mean? That is, there are d positive integers. What is the meaning of this? There are d positive integers, suppose that t1, t2, td, right? Such that c is equal to sigma I to the power I c for every I, right? What I've said, t1, t2, td are the positive integers. Now I am translating. Suppose I equal to 1. If I translate, I can see the configuration. Okay, if C is a periodic configuration, then for a given T1, if I do this translation, C will remain same. This is the meaning of invariant. I am applying one function. I am applying one translation, but C remains same. There is no change in C, right? See, in the previous example, in the upper example, I have written C dash equal to sigma 1, then C. This is a general one. If I apply sigma 1, it's shifty, no? It should change. But if it remains same after applying the translation, we call it periodic configuration. And that it is to be true for each I. It's not that it's true for only I equal to 1. No. It's to be true for I equal to 1, I equal to 2, I equal to d. So for all possible cases, this to be true. Pictorially, suppose this is a small part of configuration. Say it's a small part of configuration, right? Suppose it's a small part of configuration. Now, so I am applying T1 along with x-axis, T2 along with y-axis, right? So the new blue box, I can get from the old one, right? So if it happens everywhere, I have given in this figure, I have given only 2 examples. The small box is repeated. So periodic configuration means although the configuration is infinite, in that configuration you'll find a small part which is repeated everywhere. There's a meaning of periodic. And how it is repeated? Repeated in this way. It's not arbitrary repetition. It is not an arbitrary repetition. Repetition follows this one. That C equal to sigma I to the power Ti of C. And it's true for every I. See in the figure, first I have applied T1, right? So if I apply T1 only, I can apply T1 only. Then I can get the small box, right in the left hand side. Now if I apply T2 only, then I can get this small box, the first small box in the downward direction. And if I apply both, I can get that one which I have shown here. So actually, this is the meaning of translation. If I write it in more detailed way, then I can write what I've written before. That means C of x, vector x is the position, is actually C of x plus Ti ei for every x in x to the power j to the power d, and is for each I equal to 1 to d. And here ei is nothing but unit coordinate vector. Okay, so unit vector actually. Okay, I mean, so all at 0. So if ei equal to say it is 2d, so and for equal to I equal to 1, then 1 0 equal to 0 1 in this way. This is the unit coordinate vector. So this is the definition of periodic configuration. In short, a small part of configuration is repeated everywhere. In case of finite configuration, there is a repetition. In almost all places, Q was all places, all the cells, Q were there, Q was there. Okay, only small part was the non-quotient state, but here it is not the case. A small part is repeated in every class. Well, like before, let us consider CP to be the set of all possible periodic configurations, right? Right. So obviously the CP also proper subset of S to the power J to the power D, like before. Now, if I consider GP is a restriction of G on periodic configuration only. Okay. So domain of G was S to the power J to the power D. Now considering a subdomain which is GP. So then I can get a function. I can get a function like this. So sorry. By applying the restriction, I can get CP. Okay. So G is working on CP. If G works on CP only, let us call it GP. Then I can get this one GP from CP to CP. So this is again a new global transition function that works only on periodic configuration, right? Although I mean, in case of finite configurations, it is easy to visualize. But how can you visualize? Although I've given this definition, but how can you visualize? Let us try in a brief way. Suppose declare 2. So it will look like this one. If you consider declare 2, it will form a torus. As if, so you are, twisting the edges, opposite edges, right? Take as a A4 sheet and twist the opposite edges, right? Suppose you are say gluing the opposite edges, and then you can find this kind of circular, this kind of shape you can get, right? That's the meaning of periodic periodic configuration. Why it is so? Because after one place, after one place, the same configuration, the same state sequence or state of the cells is repeated, right? So as if your CA is running on that one, on that torus. And if you can know this torus part, you'll be able to get, able to regenerate the whole configuration, because that is repeated everywhere. In case of one-dimensional CA, it forms a circular array, right? It forms a circular array. So as a circle, an array is given, a small part is repeated everywhere. Okay, as if the circular array, it is showing the next configurations one by one. As I've said before, these finite configurations and periodic configurations, they are the important. Why? If we really want to simulate the CA on computers, then we cannot deal with infinite configuration. And in practical purpose, for simulation purpose, they are not very meaningful always to deal with infinite configurations. But CA is defined over infinite grid. So therefore, we deal with either we should deal with the finite configurations whose size is finite, and periodic configuration. Periodic configuration is again infinite, but a small part is repeated. So by starting a small part, I can get idea of the whole one. So these two are important. Okay. So next, let us move to another concept, the definition called neighborhood. Recall that the definition, in the definition, neighborhood how it was defined. It is a vector, neighborhood vector. It is V1, V2, Vm. So m number of cells are associated with each cell V of the lattice, right? That was the neighborhood vector. So in general, we can associate any number of nearby cells of any pattern. Okay, that I can do, right? But there are some two special, two popular neighborhood 2DCA. Okay, there are two popular neighborhood condition for the 2DCA. One is von Neumann neighborhood, and another is Moon neighborhood. So we now discuss this, two neighborhood structure. So this is the von Neumann neighborhood. Von Neumann developed, I have said last class, the von Neumann first developed the cellular automata, right? In that work, von Neumann used this neighborhood structure. So blue cell is a cell under consideration, and the orthogonal cells, right? So left, right, up, down, these four cells are the neighbors. These are the immediate cells, right? These are the immediate cells of the blue one, right? So this neighborhood configuration is called von Neumann neighborhood, right? Von Neumann used this one. However, after the work of von Neumann, Moore proposed a different kind of neighborhood like this one. Here, instead of orthogonal cells, orthogonal neighbors, the corner cells are also considered as neighbor of the blue cell. This is the, you can get a square-like structure, right? So this neighborhood structure, it was proposed by Moore, so it's named after Moore. So we call it Moon neighborhood. So these are very popular in all the works. Almost all works, either von Neumann or Moon neighborhood, they are considered. And you can see when we were discussing about Game of Life also assumed this Moon neighborhood, right? Means 9 neighborhood means 8 neighbors and including excluding itself. So 8 plus 1, 9 neighbor. Apart from stating the neighbors of a cell through neighborhood vector, sometimes we specify neighbors to radius. Now, in case of von Neumann neighborhood, in case of Moon neighborhood, we have seen that the neighbors are always consecutive cells, and this is the meaning of neighbor, right? So my nearby cells can be my neighbors. That is our general understanding. And in case of C also, that is assumed. So radius, what radius says? It says number of consecutive neighbors, number of consecutive cells that are neighbors of each cell, right? And in case of 2D, I can get 4 directions here. So for one cell, left, right, along x-axis, there are 2 directions, right? Left side, right side. Along y-axis, there are 2 directions, right? So in 4 direction, so number of consecutive cells, what the neighbor, that is called the radius, right? Now, in case of von Neumann neighborhood, what is the radius? Is 1, right? Because in left and right, up and down, all the cases, only one cell is a neighbor, right? And in case of moon neighborhood also, the same thing applies. Because in this case, in each direction, only one cell is associated. And you see, in case of neighbor, in case of moon neighborhood, there are 8 directions. So 4 corner directions, right? So in each direction, only one cell is associated with the center cell. So this is the radius of 1. We'll see later, CA is very regular, very uniform, right? CA uniformity is the heart of cellular automata. So when you see, when you define a neighborhood, then also you can find some this kind of uniformity. A cell under consideration, it has left neighbor, right neighbor. If there are neighbors in left, then there will be R neighbors in right. If there are neighbors in upward direction, there will be R neighbors in downward direction. This kind of uniformity is everywhere in our cellular automaton. So therefore, instead of using neighborhood vector, we can get neighbors of a cell using a radius, right? If it's 1DC, it's very simple. But if it's 2DC, now and if it is moon neighborhood, I can get the radius. Okay. Now, in case of 2DCA, you may raise this question that, well, for 1DCA it's very simple, but 2DCA there are 2 neighborhood conditions, von Neumann and Moore. If R equal 2, how will it look like? It will look like this. So first consider the moon neighborhood with R equal 2. It is obvious that radius is 2 here. You consider each direction here 2 consecutive cells are neighbors of the center cell, right? In case of von Neumann neighborhood, we consider this structure as to denote radius equal to R equal to 2. So here center cell, as if it was moon neighborhood for R equal to 1, then 4 neighbors, orthogonal neighbors, they are added here. So this kind of structure, this is a von Neumann neighborhood for with R equal to the left hand side, right? So it says that by specifying R, I can get neighbors of a cell. Now, if it is so, then radius is more appealing than using the neighborhood vector. Well, neighborhood vector has some general structure, right? So in case of 2D, I am saying there are 2 options that may confuse you. So neighborhood vector may be the generalized option, is good option, you may say. But to understand, to visualize it in better way, radius, you may prefer radius. And then, so, in our definition, we can replace neighborhood vector by radius. And you can see the many definition of CA, right, that uses the radius. Right? Especially the older definition, they always use radius than neighborhood vector, right? Okay. This is about the neighborhood. Yes.
Why the corner cells are required in von Neumann R2?
Sorry.
In von Neumann radius equal to 2 diagram, why the corner cells are required?
It is equal to diagram.
in the von Neumann diagram for r equal to 2, why we need that corner cells?
The corners one, no?
Yeah.
So actually, here I am not discussing, but see, if you in one step for the center cell, you can go to the left, right, up, down. In two step, if the distance is 2, then you can also go. Then you can go all the outer one. Okay, this is called Manhattan distance. In that case, you can find the distance is 2. The added corner cells. So that we can find the distance is 2, right? So here what I've considered. So if I no, what is that one? So if the original one, so when article to 1, so if I put this, if I mark the boxes as 1, then the rest box will be marked as 2. You in one step you cannot go there. You can think in this way, in one step. So if you want to reach to your neighbor, if you want to see the state of neighbor, right? In the distance of the nearest neighbor, there's 1 actually, okay. But what about the other neighbors? For that, you need 2 steps. Okay. So distance is 2.
Okay, so basically the maximum steps to be taken to reach any cell.
Sorry, maximum?
Maximum steps to be taken to reach any cell.
Yeah, that's the meaning of radius, no?
Yeah.
Radius is
And
there.
how? Okay. And how about this Moore neighborhood for r equal to 2?
R equal to in each direction you can see is at most 2. So corner, in corner direction is 2, and in left, right, up, down is 2 cells are there. Okay.
What about the second cell from the top left, means the down, the first cell of the second row, first cell
Yeah.
of the second row in the
First cell
of the
first cell of second
second.
row, or the second column of the first row. Okay.
Yeah.
Right.
Yeah.
So here what I'm considering, see that in the radius 1, so all the if you mark them 1, na, so in the next step, how much cell you can cover, which cells you can cover, right? So you can cover the the top cell, topmost corner cell, right? And topmost left corner cell, topmost right corner cell. In this way, you can cover all the corner cells, right? And then also, if you go along the x-axis, you can consider that cell also. Then what about the remaining cells? They come under that one. In that step, you also will be able to reach that cells, those cells. Okay. Here also distance is also 2.
Yeah. Yes, got it.
Okay. Now let us move to a special class of cell automata called elementary cell automata. So today what we have discussed till now, we have discussed configurations, finite configurations, periodic configurations, and the neighborhood. Last class we have discussed about game of life, a very popular cell automata. Today we are going to discuss about a special class of cell automata, very simple cell automata. It's called elementary cellular automata. Its name is elementary. So we'll see that how simple it is. Its specification is like this: D equal to 1. It's a binary system, binary cell automata. I mean, so it defines over Z, right? Is equal to 0 and 1, and aim the neighborhood vector is equal to -1, 0, 1. That means a cell depends on itself, its left neighbor, and right neighbor. And it means radius is equal to 1, r equal to 1. And obviously the rule h to the power 3, because 3 neighborhood dependence is there, h to the power 3 to s. So this is the array of cells. Say, you can consider an array, one-dimensional array, right? So black cell is here in the figure. Black cell is the cell under consideration, and the gray cells, they're its neighbors, right? So one it's left neighbor, the left side neighbor is the left neighbor, right side neighbor is the right neighbor, and the self. So -1, 1, and 0. It's neighborhood vector, right? Actually, this cell automata was first studied by Stephen Wolfram. Okay, Stephen Wolfram first studied this kind of CA, and in 1984 he wrote a paper on statistical mechanics of cell automata. And nowadays, the major share of CA research, major share, is with this elementary cellular automata. Most of the people who work in the domain of theory and application of cellular automata, they deal with elementary cellular automata. Although before Wolfram, so many classical works were there, starting from von Neumann's work, Moore work, then E.F. Codd was there, then Game of Life was there, but systematically explored, the CA was systematically explored by Stephen Wolfram, and for that he considered this simple one, this simple system of cell automata, right? Now, in that work, actually, the statistical mechanics of cell automata, he represented ECA rules in a special way, in tabular form, in this way. See, I think you'd appreciate the simplicity of that one, of these ECAs. See, ECA rules are presented as a tabular form. Why it is so? See, there are only 3 neighbors. Suppose X, Y, Z, they are my 3 neighbors. My rule is R, right? R has 3 arguments. It takes 3 inputs. Suppose it is X, Y, and Z. Now, since my system is binary, X, Y, Z, they can be either 0 or 1. Let me write down the all elements of domain. Right? The element will be 0, 0, 0, one element of the domain, 0, 0, 1, right? In this way, 1, 1, 1, right? So there are 2 to the power 3 elements only in my domain of R, right? When I'm presenting the rule, I am writing the domains in fashion. So in the figure, what you are seeing here, the topmost row, it notes down the domain values, right? Domain of the rule, right? So, and this is my style. I shall start from 0, 0, 0, 0, 0, 1 to 1, 1, 1, right? Now, for each domain, value, for each 0, 0, 0 or 0, 0, 1, I can get a rule value. I can get R value. Okay. So I am writing the R value in the 3rd row. Look at the figure. Look at the table. I've written R X Y Z. So it shows if R X Y Z all are 0, then it is 0. This is one rule. Okay. So please consider the first one. First blue line. So x, y, z, they are 0, 0, 0. Then r, x, y, z is 0. Let's say it is 0, 0, 1. Then r 0, 0, 1 is equal to 1. In this way. Okay. So similarly, r 1, 1, 1 is equal to 0. So I can write down these r values, the function values, against the domain one by one. Then what do we get? We get a 8-bit binary sequence, right? And from the 8-bit binary sequence, I can get a decimal number. Wolfram proposed that name the rule with that by that number. This is the proposal of Wolfram. So this kind of rule, this kind of notation, sometimes called as Wolfram's rule. Okay. So the first one, the first rule here I have written 0, 1, 0, 1, 1, 0, 1, 0. It's called rule 90. This is nothing but the decimal representation of 8-bit binary sequence. See how I shall write the binary sequence that is specified. What I've shown here, you have to follow this style only, right? In the LSB 000 and MSB 111, and then you'll get a bit sequence against a rule, and then name the rule by the decimal equivalent. I mean, the decimal equivalent of that 8-bit string. So this is the rule 90. The next one, I can get another rule. So where r 0, 0, 0 is 0, 0, 0, 1 is 1, and say r 1, 1, 1 is 0, etc. So look at the next rule. I can get a new binary sequence, which is actually another rule. So it's rule 30. Okay. So Wolfram proposed to represent the rules in this fashion, right? Since system is binary system, and since it is 3 neighborhood system, only x, y, z, so 3 values are there. So it's possible to represent the rules in tabular format. And here there are only 2 to the power 3, 256 rules. And rules are numbered. How they're numbered? Rule 0, all 0, rule 0, rule 1, rule 2, up to rule 255. Right? So these are the rules. Although this style is very good, but you understand, instead of 3 neighborhood, suppose m equal to 5, say 5 neighborhood, means r equal to 2. Then in the domain, how much element you'll have? 2 to the power 5. That is 32. How many rules you'll have? 2 to the power 32. That's a huge number. That is difficult. That is really difficult to deal with. The interesting point is, for ECA there are only 3 values, 3 input values. So there are only 256 number of rules. So this number is really manageable. So Wolfram use this style. So in our further discussion, when you say ECA 90, rule 90, so rule 10, rule 110, 110, rule 240, etc., will mean that ECA rule of 240, say, of 90, which is represented in this format, right? Okay. And you would appreciate, I think all of you will appreciate that ECA they are very easy to implement, very easy. So one dimensional, only one dimensional binary, they are very easy to implement, and this is one reason why they are so popular. I mean, you'll explore later that how important, how beautiful they are. Very, very simple system, right? A cell is very short-sighted. It can see only its left neighbor and right neighbor, nothing else. And its state is only 2, 0 and 1. With this simplicity, you'll observe how beautiful pattern, how complexity it can generate. It's amazing. Let us start with ECA 90. So we want to see the evolution of ECA 90. Okay, means the first rule in the table. In the table there are two rules, 90 and 30. So start with the first rule. Evolution means what is the meaning of evolution? So in case of cellular automata, time and space both are discrete, and in next time step, so all the cells apply the rule. It goes to the next configuration, then next to next configuration in this way, right? So time moves, and that's called the evolution of a CA. Okay. You can observe that in case of ECA 90, 0 cohesion state. The same is for 30 also, right? Here 1 is not cohesion state, but 0 is cohesion state. Why? What is the definition of cohesion state? That R of say Q equal to Q. Here R of 0, 0, 0 equal to 0. For 90, 90 of 0, 0, 0 equal to 0. 30 of 0, 0, 0 equal to 0. So for 90 and 30, for both the cases, 0 is cohesion state. So I can deal with finite configurations. Presence of cohesion state tells us that okay, we can deal with finite configurations. I mean, it doesn't matter, as I've said before, it doesn't matter that your state set will have always a cohesion state. If you don't have cohesion state, you cannot get the finite configurations, right? So here I'm getting cohesion state. It's possible to get the finite configuration. Let us start this let us start my automation from this configuration. Since all are in all zero configuration, only one cell. See, look, the middle one, its state is 1, right? So therefore, this configuration is a finite configuration. Okay, one cell is there. All but one cell are in cohesion state, right? So only one, that cell, the middle cell here, I'm calling it middle cell. Okay, I'm calling it middle cell. So that is in non-cohesion state, right? So as if system was stable, cohesion state indicates stability of the system. Only one noise is created. So one represents a single noise, as if a noise is added in a cell. See what happens now. So this is our initial configuration. Now, if I apply R everywhere, what I will see? See, the 1, this 1 becomes 0. Why? Because if the middle cell applies R, its input is 0, 1, 0. Because left side state is 0, its own state is 1, and right side state is 0. So 0, 1, 0. Go to the table. You look at the table. What you see? 0, 1, 0. It is 2. Is actually 0, right? R of 0, 1, 0 in case of rule 90, it is 0. So middle cell becomes 0. However, left cell as well as right cell of the middle cell, they become 1. Why? The reason they can get from the table. From that one actually, why it is so? So you look at a table, say for the Next, the right cell, right of the middle cell, its input is 100, and the table I get 100, it is 1, as well as 001, that is also 1. 100 and 001, they are both are 1. And here what I get, you can see that left cell, left as well as right cell of the middle cell, their inputs are 001 and 100. So both of them become 1. Please see it. Let me know if any doubt is there. It is simpler than game of life, much simpler than game of life. Okay. So what I'm getting here, I'm getting in initial configuration there was a single one. Now here two ones. So size of my final configuration then increasing. Okay. Now the next one. Come to the next one. Then you can see that two ones, they further moved right direction and left direction, as if they're running, going away from themselves. Right? So same rationale you can see. You can, if you apply the rule, you can get this configuration. So it is number, step number. If I start from time 0, then time 2 is time 3, then time 4. Here I can get, see again the outer ones, they are going out, but in between two more ones are generated inside one. One more thing you can see, that although you have started a finite configuration of size 1, but size of finite configuration is increasing, right? Size of finite configuration, that is increasing in this way, right? Now you, I shall encourage you to do it by your hand and see what is happening, right? Few more steps, and if you look the pattern now, if you look the pattern, you see from single one a triangle like shapes are formed, right? So one, so from one single one, two ones are generated in next time step, and they are going out. I mean, so they are moving in outward direction.
In the third line, instead of 10001, should not it be 10101?
1000001.
Instead of that, should not it be 10101? Because we are converting. Yeah, we are converting
Which
0
line?
1
Third or fourth?
third.
Okay.
10001. I was expecting to be 10101.
Sorry,
10101.
Yes, third to fourth line.
No, in the third line, my question is basically in the third line, I have 10001. So should not it be 10101? Because in the previous step, in the second line, we have 010. So that 010 will translate to 101. So we have both 2010. So the middle 0 should not be converted to 1.
No, for the middle zero, if you consider in the second step, for the middle 0, its left neighbor was 1, right neighbor was 1. Okay, so its input the function is 101, right? Go to the table. 101 for rule 90, it is 0. Can you see?
101. Yeah.
1 0 1 5 5. It is 0. So it should remain 0.
Oh, okay. Okay.
Okay. So in this way.
Uh, okay. Yeah. Yeah.
Yes. It's okay or no?
Yeah. It's okay. Yeah.
Okay. Well, so in this way, I can get the configurations one by one. Now, if I run it several times, there are only 4 5 times I've done, 3 times, I've run for tries. So it's equal to 1 2 3 only. If I run it 100 times, if I run it 1,000 times, what will happen? So it's infinite. So in each step, the ones are going out in one step left and one step right. Let us see. Interesting thing you can see, I'm getting this kind of pattern, right? See, what is this? A self-similar triangles are formed. They are equilateral triangles, as if triangles. So we are researching the triangles. This kind of self-similarity is everywhere in this diagram. And this diagram is called Pascal triangle. So this kind of complex structure, I don't know whether you call it beautiful or not, but this kind of complex structure, you can also call it chaotic structure, you can get from the evolution of EC90. Apparently EC90 was very simple, right? Apparently EC90 is very simple. And if you look at the table now, then EC90 is nothing but it just adds left neighbor state, right neighbor state, and do the modular operation. Actually, it's the XOR of left neighbor and right neighbor. You can see from the table, if you derive the function, you can see that this rule 90 is nothing but XOR function it runs. It uses. I mean, XOR of left neighbor and right neighbor. And by applying XOR in that fashion, I can get this structure. This is the beauty, you can say. This is importance, you also consider, of elementary cellular automata. Let us take another example for rule 30. See, if you take rule 30 here, then there are less patterns. Although you can find equilateral triangles, in some equilateral triangles are there, but it is not so beautiful like the previous one. It is not like EC rule 90, but still you have the triangle. So, in some sense, this pattern is more chaotic, more random, right? And it means it is having less pattern. In the previous case, we have many patterns. High patterns were there, Here, although you can find some patterns, but less patterns are there. So simple change makes so many difference. And this kind of diagram, we shall call it space-time diagram. This diagram in the last slide also I have shown some diagram, and this is other diagram. So consecutive configurations are plotted against time. Okay, this is called space-time diagram, and space-time diagram of an automaton tells us many things, many behavior. Ultimately, CA will evolve with time. Ultimately, it will generate the pattern. It will generate some configurations. Whether in the configurations there are some pattern or not, that is, that you can observe from this pictorial presentation. So, space-time diagram is a pictorial presentation of evolution of a CA, and it really helps to identify its inherent behavior. So, in our further discussion also, we shall use space-time diagram to characterize a cellular automata. Especially the space-time diagram, we use space-time diagram for 1D CA. Theoretically, actually space-time for d-dimensional CA, it is a d+1 dimensional diagram, because for d-dimensions we need, and time is another dimension. So d+1 dimension diagram. So space-time diagram for d-dimensional CA is a d+1 dimensional diagram, because we add time. But practically, we'll see. I mean, in most of the cases, the one for 1D CA, we use space-time diagram. Now, this is an exercise. You do it and check. So evolve ECA 30 for 1,000 times, 10,000 times. It may be 1,000, maybe 10,000, maybe 1 lakh. That's your choice. So I've given 10,000 times. You run. And from this initial configuration, single one, set middle cell, right? And then collect the bit from the middle cell. So it will start from 1. So it will start from 1. Okay. So middle cell. So if there are 10,000 evolution, so you'll be able to collect 10,000 bits, right? So you'll get a sequence of 10,000 bits, and then you test if you find any repeating sequence. Okay, that you do. That you do by yourself. So, and if you do it by yourself, you'll observe an amazing result. I can tell you the result, but you'll observe an amazing result. That even if you run say 10,000, 1 lakh, 1 crore, 1 billion, the result will continue. What is the result? The sequence of bits, they don't repeat. The sequence doesn't repeat. So always, if you run it, you'll get a unique sequence actually. Okay, it's like pi. Okay, you know the pi, there's an int actually. There's an int, and there is a repeating sequence in this pi. So same kind of thing you'll see here. Based on this observation, but I'll encourage you to do it by yourself. Otherwise you will not fail. From this observation, Wolfram proposed ECA 30 to use as serial random number generation, and to use it in cryptography. Okay, so the style is from evolve it, and from one evaluation you collect 1 bit from the middle cell. Right, very interesting result. So these kind of interesting results we can find. So Wolfram, there is a book called New Kind of Science. In that book, Wolfram shown all kind of Wolfram experimented with all rules from rule 0 to rule 50, 255. So and he experimented with this kind of initial configuration where all 0 and single 1. I mean, it is having a single 1 and rest are 0. So one starting point. Also, he experimented with random initial configuration. Okay, and based on that, he classified the CA. Okay, and he classified in this way. He classified. He identified 4 classes: class 1, class 2, class 3, class 4. Class 1 CA, class 1 CA, they evolved to homogeneous configuration like rule 0. After some time step, it reaches to all 0 or all 1, but very homogeneous configuration. Okay. Class 2, so class 1 CA, they are very simple. They don't have this beautiful structure. So class 2 CA, they are also simple. They evolve to periodic configuration. So as it's a blink, so all 0 to all 1, like that one. Okay, but some periodic configurations, it reaches to. Third and fourth, they are very important. Wolfram observed that a group of automators and CAs, they show chaotic behavior, like rule 90, rule 150, rule 60, rule 30, rule 45. They have excellent behavior. This kind of properties there. They show the chaotic behavior. They show chaos. And fourth one will be the most interesting one: the complex structure. Although I don't have slide here, and I shall cover. I don't know how much I'll be able to cover in this course. But just for information, Wolfram claimed and later it was proved that ECA rule 110, it is computationally universal. That is, it is as powerful as universal Turing machine. Amazing result. So using this kind of structure, simple binary structure, 1D array, that can emulate a universal Turing machine, means what your computer can do, that can also be done by that 110, a simple rule. Okay. Anyway, there are 4 classes. I have just stated the name of the classes. What is chaos? What is the chaotic behavior? We shall discuss in this course. What is computational universality? That also we'll discuss. They will be discussed later. So here I have given just the specification and stating that the simple structure can show this kind of interesting behavior. And these are the reasons why EC are so popular. They are very simple. They are easy to implement. Still, they show this kind of properties. So some people argue, if EC can do all these things, including universal computation, why should you look at other complicated cellular automata? Okay. So that's all for today. And let me know if you have question.